Okay, our next topic is going to be a brief excursion into the topic of Cmos digital circuit design. This would be things like logic gates, things like simple 1-bit storage elements, things like that. We're not going to be going into this super deeply, but it would be good for you to have some basic understanding of how these things work down at the transistor level based on your newfound knowledge of how the Mos transistor works. So the first thing to talk about is a representation. And that is, we're going to be using a logic 0, represented by ground, and logic 1, represented by VDD, which might be in our case plus 5 volts, but in more modern systems it might be 3.3 or 2.5 or 1.8, something like that. A lot of digital circuits nowadays, FPGAs and microcontrollers and things like that, are running with something like a 1.2 volt core and IO pins that can go 0 to 3.3 or something like that. But for us, we're going to be using 5 volts as our power supply like we have been. This isn't the only possible representation. We could take logic 1 to be ground and logic 0 to be VDD. That's a perfectly valid way of doing things. It's a little unconventional, but if you're consistent about it, there's no reason why you couldn't do that. And so with that in mind, what we want to do is talk about so just different basic configurations. So let's suppose I have an NMOS transistor like this, and I have a logic signal, which I'll call A, into the gate, and then I consider, let's see, I'm going to call this side U, and I'm going to call this side V. So I'm not going to tell you which is the source and which is the drain. These are both source-drain regions, and which one serves as source and which one serves as drain depends on which of these two is at a higher potential. Okay, but what I want to focus on is under what conditions, if A is a logic signal, are U and V connected to each other? Well, U and V are connected in this case if A. So if A is true, then U and V will be connected because A has a gate voltage of VDD. Okay, and if A is false, then U and V are not going to be connected. They're not going to be connected by a nice low impedance or low resistance path. Okay. Likewise, if I had a PMOS transistor in a similar kind of situation, and I had, giving myself quite enough space there, move this down a little bit here. If I have my PMOS transistor with the gate signal A, and I have U and V on each side, well, in this case I get U and V are connected if A is low, right? So if A is ground, then U and V might be connected together by a low resistance path. So we could represent that by saying if not A. So the nomenclature, or the notation I'm going to use for Boolean expressions is the one that I think is commonly used in our computer architecture class. So if you haven't had computer architecture yet, that's fine. This overbar basically means not. Okay? And we're going to use like a plus sign for logical OR, and we're going to use effectively like a times sign for logical AND. Okay? So, but the point here is that U and V are connected if not A. And so the bubble in logic gate symbols usually represents inversion, like an input is inverted, and that's true here in this case with a PMOS transistor too. So A going into the gate of a PMOS transistor means that the conditions under which the two sides of the transistor are connected are basically not A. Okay? So that's one transistor. What happens if we put, let's say, two transistors in series? Let's say two NMOS transistors in series with each other. Let's say I have A and I have B, and I have my U and V. Okay? So in this case, since these two transistors are in series, if either one of them is turned off, is not conducting, then the series connection of them is also not conducting. So if both of them are not conducting, I'm not going to get any connection between U and V. If A is not conducting but B is, I'm still not going to get a connection because these are in series. Likewise, if B is conducting but A is not conducting, then I'm not going to get a connection. And that's going to correspond to logical AND. So I need A and B in order for U and V to be connected. So U and V are connected if A and B. Okay. Well, how about two transistors, two NMOS transistors in parallel with each other? So I've got A up here, and I've got B down here, and I've got U and V. Well, in this case, U and V are going to be connected if A is conducting, or B is conducting, or both are conducting. Right? And that's going to correspond to the logical OR, the inclusive OR, which we denote by A plus B. Right? So this is AND, which is conjunction. And this is OR, which is disjunction. Well, how about PMOS transistors? So suppose I have my two cases with the PMOS transistors that are corresponding to these two cases with the NMOS transistors. So let's suppose I have two PMOS transistors in series, A and B in the gates. Well, in this case, I need A to be low, and I need B to be low in order for there to be a connection between U and V. So U and V are connected if not A and not B. Okay? So we need to have A being low and B being low in order for U and V to be connected. Now there's a well-known theorem or law in Boolean algebra called De Morgan's law, actually one of two different variants on De Morgan's law, and I forget which is which. But this, by De Morgan's law, can be written as A nor B. Okay, so this is one of De Morgan's laws. And this is basically nor, not or. So this series connection here would correspond, with the bubbles and the gates, would correspond to a nor condition. Well, what about the parallel connection? AB and U and V. Well, in this case, U and V are connected. Well, I can either have not A, or I can have not B, or I can have both not A or not B. So the condition here is not A or not B. And by De Morgan's other law, there are basically two of them, we can basically make this Nand. So De Morgan's laws work like this. OR switches to AND, or AND switches to OR, and the complementation pops up one level, or pushes down one level, depending on whether you're going this way or that way. So this is De Morgan's other law, and this is Nand. So here, these things, A, not A and B, A or B, A nor B, or A Nand B, are called the conduction conditions for each of these networks. Okay, so these Boolean expressions that are true when the network conducts and are false when not, are called conduction conditions. Okay, and here we have this notion in these sort of four cases with the two transistors in series or two transistors in parallel, that parallel corresponds to OR, because there's two different pathways that we can go in, and if either one of them is conducting or both are conducting, then the overall parallel connection is conducting. And the series connection corresponds to AND, because I need to have both of these things conducting in order for the series connection to be conducting. And so we can sort of generalize this beyond the individual transistor level to sort of subnetworks as follows. So if we have some, let's say, some network whose conduction conditions are given by, let's say, some Boolean expression P, and some other network of transistors whose conduction condition is represented by the expression Q. If I put these two in parallel, and I say this is U and this is V, well, U and V are going to be connected if P or Q. And so these represent expressions or sub-expressions that are the conduction conditions for whatever is in this box. And so the overall conduction conditions for these two networks in parallel are given by P or Q. Okay? And likewise, if I have a series connection of these same two networks, P and Q, we have U and V. Here U and V are connected if P and Q. So in general, we have basically series goes with AND, or conjunction, in parallel goes with disjunction. Okay, so those are going to be important concepts for us here. With that in mind, we're going to look at the structure of what's called a static complementary Cmos logic gate. And this is sort of the vanilla Cmos logic family. Okay, and the basic idea is that we have two networks called PUN and PDN. And on one side of the network we have the pull-up network. That's what PUN stands for. So this is the pull-up network. And this is the pull-down network. So up here we have VDD. That's one end of the network. It's connected to VDD. The other end of the network is connected to the output of the gate, which is usually called Y. So this is the output. And the one end of the pull-down network is also connected to the output of the gate. And then the bottom of the pull-down network is connected to ground. And we've got some inputs that come in here. A, B, C, and the same inputs go into, in general, the pull-down network A, B, C. And so this is the structure, or the topology, of a generic Cmos logic gate. Let's get the pull-up network and the pull-down network. The pull-up network, for obvious reasons, is called the pull-up network because what its job in life is to pull the output of the gate up to VDD. The pull-down network is, its job in life is to pull the output of the gate down to ground. And so these networks are responsible for, respectively, producing a logic high on the output of the gate or producing a logic low on the output of the gate. So the pull-up network, let's say this has the conduction condition. We'll call the conduction condition for the pull-up network, we'll call that U. We're only going to make the pull-up network from Mos transistors. Okay, that's a discipline that we're going to impose on our design of logic gates for reasons that you're going to explore in post-lab 5. So I'm not going to tell you why we adopt that design discipline, but we do. So we only want to pull up with PMOS devices. And for the pull-down network, we'll call the conduction condition D. So this is up and down. And we're only going to make the pull-down network from NMOS transistors. So again, our discipline that we're adopting for the design of these kinds of gates is that we're only pulling up with PMOS devices and we're only pulling down with NMOS devices. And again, that's something that you're going to be thinking about for post-lab 5 based on your simulated transistor characteristics that you're investigating in lab 5. Okay? So we say if it's true, so in general, we don't want, we never want U and D should be false. Okay. So actually I'm running out of space here. I think I'm going to go over here. So we want, in general, we want U and D to be identically 0, right? And the reason for that is if U and D were true under certain conditions, then that would mean that the pull-up network and the pull-down network would be conducting at the same time, which means that I'd have a nice low resistance path between VDD and ground, and that would result in excessive power consumption, potentially large currents flowing from VDD to ground, so that otherwise we have a low, say, conducting shorting VDD and ground. So we might have a situation where some of these signals are going from low to high or from high to low, and we have sort of both of these two networks on at the same time, partially, and that would cause a transient sort of increase in current and a transient power increase. But what we don't want is we don't want a sustained period of time where these networks are both on all the way. If you and let's see, what is it? If it's if U and D bar is true, then the gate is said to be combinational. So basically what this means is that either, I think it's actually, maybe it's U or D. Actually. So if there are no circumstances under which the pull-up condition or the pull-up conduction condition or the pull-down conduction condition is false, then you either have the pull-up network conducting or the pull-down network conducting under all circumstances. And so the output of the gate is always driven either to a logic high or to a logic low. And it's never sort of disconnected from either of the two rails. So it's never output is always driven. If there are times during which neither PN or PD is conducting, the gate is state holding. So what that means is if there are certain periods of time when the pull-up network is not conducting and the pull-down network is also not conducting at the same time, that means that Y is basically disconnected from the power supply rails through these networks. And so Y has to hold its state. And so Y has to remember its previous value somehow. And that could be just that there's some capacitance on this node like we've talked about before, and it's been set at some voltage and there's some charge on that capacitance, therefore. And during that sort of state holding phase, that charge will sit there on the capacitance, and as long as we don't disturb it somehow, that voltage will be maintained there. But that becomes what's called a dynamic node, and it's liable to be something that doesn't stay put. Leakage currents, capacitive coupling from other nearby wires and lines and things like that can disturb the node and corrupt the actual value of the gate. Okay, so we'll see some examples of state holding gates eventually, but we're going to talk about combinational gates primarily today. Okay, so simplest of all logic gates has, so this is going to be the Cmos inverter. Simplest of all logic gates. Basically, it implements the logic function, let's see, y equals not a. Okay? And the way this works is that U, so U is, and that should be, U should be the function we're trying to implement, and D should be the complement of what we're trying to implement for a combinational gate. And so we can take Y as the conduction condition for the pull-up network directly. And so not A, we already saw a network of Pmos transistors that would be suitable for that. It's just a single Pmos transistor. And so this would be the pull-up network for our Cmos inverter. This is Y. And the pull-down network would just be, D would just be not A, or A. And so the pull-down network is also a single NMOS transistor. We've already seen that one. And so these are tied together like so. And we have A going in to the two gates of these transistors. This is the pull-up network. This is the pull-down network. And typically in logic circuit diagrams or logic circuit schematics, this would be the logic symbol for an inverter. So this is the logic symbol. That's in common use. And this would be the transistor level schematic. So if A is 0, or logic low, well, we've got VDD on the gate, we've got ground, we've got VDD on the source of the PMOS transistor, we've got ground on the gate. That means that this transistor is on, It's high up in strong inversion. And at the same time, we have the gate of the pull-down transistor being 0, the source being 0, so it's going to be as off as we can make it. It's going to be way down in weak inversion, so we're going to say that's off. And so we're going to have a nice solid connection between VDD and the output. The output's going to get pulled up to VDD, and the pull-down network is not going to be opposing that. If we put a logic, I'm going to use a different color here. If I were to put a 1 in for A, well, this would be up at VDD, okay, the gate of the PMOS transistor, so there's no source to gate voltage here. And so this transistor would be off, really down in weak inversion with very little current. And this transistor is going to have the opposite condition. It's going to have its highest gate voltage, and the source is at ground, so this transistor is going to be really high up in strong inversion. It's going to be on. And there'll be a nice solid connection between the output and ground, so Y is going to find its way down to ground, and it's not going to be opposed at all by the pull-up transistor. Okay, so that's a Cmos inverter. We'll talk a little bit more about the voltage transfer characteristic of the Cmos inverter as sort of a prototype for logic gates. We sometimes will also talk about something called a truth table, and so the truth table for this circuit would be something represented like this. So we have a table that gives the possible values of the inputs. In this case, there's just 1, 0, and 1, and then the value y. So y, when a is 0, not 0 is 1, and not 1 is 0. So this would be the truth table. All right, so let's talk about maybe a slightly more interesting gate. How about a 2-input Nand gate? So Nand 2. In this case, y would be equal to AB bar. So just like in ordinary sort of algebraic equations and Boolean algebraic expressions, we will sometimes drop the dot and just denote sort of the conjunction by putting the two Boolean variables next to each other like we would in ordinary multiplication. And so in this case, U, the conduction conditions for the pull-up network, would be, again, Y, which is A, B bar. But by De Morgan's, one of De Morgan's laws, we can rewrite this as, we can push this overbar down onto the Boolean variables themselves and switch the conjunction to disjunction. So A, B bar becomes not A or not B. And D would be Y bar, which would be AB bar bar, and the double complementation goes away and we just have AB. And so we can read the network topology directly off of the conduction conditions. So I should say that for the pull-up network conduction conditions, what we would like is we would like all of the best situation would be that all of the Boolean variables in the expression are complemented, because that is directly implemented in PMOS transistors by the bubble on the gate. It comes for free. And for the pull-down network, likewise, we would like all of the Boolean variables to be not complemented, because the NMOS transistors don't have a bubble on the gate. If we wind up with some sort of mixture, then that suggests that the gate will require both signal and complement probably, and we would have to generate that with some sort of extra CMOS inverters off to the side. Okay, so with these two conduction conditions, we can design our gate. So I guess I should say the truth table for this would look something like AB, Y, and so we get 0, 0, 0, 1, 1, 0, and 1, 1. And then for Nand, it's not and, so it'd be a 0 here, a 1 in each of these 3 rows. And the logic symbol that's commonly used for Nand 2 would look something like this, with a bubble on the output. And so we can design the actual transistor level implementation of this gate. So the pull-up network, we've already met this pull-up network before. It looks something like this. The 2 Pmos transistors arranged in parallel. Connection up to VDD. And then the pull-down network would just be 2 transistors in series, 2 NMOS transistors in series, which we can draw something like this. So this would be A, B, and Y. And so you can check the truth table here if you like. So if we make A 0 and B 0, both these transistors are off. Both these transistors are on. And so the pull-down network is cut off, not conducting. The pull-up network is conducting as much as it can be. We'd expect the output to be connected to VDD. If we make, let's say, A1, what would that do? That would flip this transistor to on. That would make this transistor off. And so we still have the pull-down network cut off because we have one transistor on, one transistor off. But the pull-up network is still conducting through the B side. So Y is still going to be 1. So that's the second row. Or no, actually that's the third row of the truth table. If I instead make A0 again and B1, this would be the second row of the truth table. This one goes on, this one goes off. Off, on. So the pull-down network is cut off in this case still, because one transistor's off, one transistor's on, and the pull-up network is still conducting because one of the 2 transistors that are in parallel is conducting. And so that would leave Y1 in the second row. And if we go down to the last row, which is both A and B are 1, well, in this condition, both the pull-up transistors are going to be off, and we're going to have both pull-down transistors on. And through the pull-down network, the output of the gate is going to be connected to ground. Okay, so that's a 2-input NAND gate. How about a 2-input NOR gate? So in this case, Y is A or B bar. Well, U is Y, which is A or B bar. And we can use De Morgan's other law and push the over bar down onto the Boolean variables and change the OR to an AND, like so. And then D becomes not Y, which is A or B bar bar, and the double complementation disappears and it becomes A or B. And so we can read the topology of the pull-up network directly from this expression, topology of the pull-down network directly from this condition, And so I guess we can draw the schematic first. So in the pull-up network, we have VDD, 2 transistors in series, like so. The pull-down network, we have 2 NMOS transistors in parallel. It's the output of the gate. This is A. This is B. And this is the output of the gate Y. And so the truth table here for Xor Gate, ABY 0 0 0 1 1 0 1 1. So not or would be a 1 up here and 3 zeros here. And then the typical symbol we draw for a 2-input Xor Gate looks something like this. And we can check this out again against the truth table. We're not going to do this for all of them, but maybe for a couple of examples it's useful to kind of go through it. So 0 0 is the first line. Well, if I got 2 zeros, then both of the NMOS transistors are off, and both of the PMOS transistors are on. And so I've got a nice low resistance path from VDD to the output. The output is pulled high. No opposition from the pull-down network. Both branches of the pull-down network are cut off. If I switch B to 1, now I'm just going to the second row of the truth table, that flips this transistor to on and this transistor to off. And so I've got the pull-up network now cut off because one of the 2 switches is off. And I have one of the 2 pull-down transistors which are in parallel turned on, so there's going to be a conduction through the pull-down network, pulling Y low, unopposed by the pull-up network. If I switch A to 1, that flips this transistor to on, this transistor to off, and then I switch B to 0 to get to the third row of the truth table. That means this transistor is now off and this transistor is on. I have, again, a case where one of the 2 transistors in the pull-down network is conducting, pulling the output low, unopposed by the pull-up network because one of the 2 transistors that are in series is cut off, so the series connection is cut off. And so the output of the gate should still be low. And then the last row is 1 1. Now both pull-down transistors are on and both pull-up transistors are off. So the output of the gate is pulled low through both conducting paths, and so it's a slightly more solid connection to ground than it was in either the first 2 0 rows in the truth table. Okay, so that's kind of how these simple gates work. You'll notice that these 3 gates have been inverting, right? So we looked at the inverter, we looked at the Nand 2, the Xor 2, and these have all been inverting gates, and they've been very convenient to implement. Let's try implementing a 2-input AND gate and see what happens. Okay, so how about AND 2? And this would be Y equals AB. Okay, so in this case, the pull-up conduction condition would be Y, which is AB. Unfortunately, because the pull-up network has the bubbles on the gates, because it's made from PMOS transistors, we're going to have to do something kind of weird. We're going to have to double complement these things. So this is the same expression, but one option would be to double complement them so that we have the signal going into the PMOS transistor. Well, actually, maybe I don't want to explain it that way. Let's just go with A, B, and D, which would be not Y, would be A, B bar, which we can write with De Morgan's law as not A or not B. So here we have a situation, which I was trying to get at, where we have the complemented variables in the pull-down network and the uncomplemented variables in the pull-up network, which means that we're going to have to actually put A bar into the gate of an NMOS transistor and B bar into the gate of a PMOS transistor in order to account for the bubbles that are in inconvenient locations. So here, what we would find is we would need something like, let's see, the pull-up network is 2 transistors in series. And then the pull-down network is 2 transistors in parallel. And what we would have to put in here are basically A bar and B bar. And the output of the gate would be Y. And so that means we would have to have an inverter, if we just had A, to generate A bar, and we need another inverter to generate B bar to put into here. So we would need sort of one stage of inversion to get A bar and to get B bar from A and B in order to implement our 2-input AND gate. Another approach would be to say, well, we know how to make a Nand 2, right? So we already did that. Another approach would be to say, well, we could take our 2-input Nand and stick an inverter on the output of it. Like so. And so, you know, we have these two different approaches. This was another approach. Generally, this one is probably preferable in terms of just transistor count. So our 2-input NAND gate was similar in terms of transistor count to this structure here, so 4 transistors, and then we've got 2 for each of these 2 inverters, whereas over here we've got 4 for the 2-input NAND gate and 2 for the output inverter. There are other reasons that we might choose to do this over this as well, one having to do with the fact that that this pull-up network here has 2 transistors in series, whereas the pull-up network here in this inverter only has 1 transistor, and that basically means that the drive strength of the thing that's driving the output of this gate and possibly fanning it out to many other gates is going to be higher, especially on the pull-up. So this gate will probably wind up being somewhat faster than this approach would be as well. So all this to say that CMOS logic is inverting. That basically means you can only implement in one stage logic functions that are inverting. And that's because we pull up with transistors that are on when the gate is low. And we pull down with transistors that are on when gate is 1. And so when you have that general arrangement, it will take at least 2 stages of logic in order to generate a function like AND or OR, which are not inverting. You either have to provide complemented inputs to the gate, or you have to complement the output. So here, the logic symbol would be this for a 2-input AND. Okay. So we can do 3-input gates. Maybe I'll do one 3-input gate before we move on to more less standard gates. All right. So suppose we wanted to do like a NOR 3. And this would be y equals A or B or C bar. And so I'm not going to draw out the truth table, but the typical logic symbol for something like this would be same sort of symbol for a NOR gate with 3 inputs, A, B, C, and Y. And here our pull-up conduction condition, U, is going to be Y, which is A or B or C bar. By De Morgan's law, this can be rewritten as A bar, B bar, C bar. And D, which is Y bar, is A, B, C double complemented, which is just A or B or C. And so again, we can read the pull-up and the pull-down network directly off of these conduction conditions. So our pull-up network is going to be 3 transistors that are in series with each other. I'll draw them all on one side here. And then I'll just draw it like this. So A, B, C. And then the pull-down network is 3 transistors in parallel. A, B, C. And then this is Y. Okay, pretty straightforward. If we had some other weird thing, like, I don't know, non-standard. Gate. I suppose we had something like the function y equals AB bar or D bar, something like that. So it's not a standard function that has a name. Maybe I'll just use C instead of D. Well, since we're using D for our pull-down conduction condition, so in this case, U would be, again, Y, which is A, Nand, B, or not C. which we can apply de Morgan's law to this. First disjunct, and that would become A bar or B bar or C bar. And D would be Y bar. And again, we can use de Morgan's law to push down the this long over bar down one level, and so the OR becomes an and so we get A, B bar bar, and C bar bar, which is just A, B, C. So I may have just fooled myself, because this turns out to be probably a pretty standard gate. This is a Nand gate. This is a Nand 3 gate. Yeah. So this is not a non-standard gate. This is Nand 3. Sorry about that. So a Nand 3 would be something like this: A, B, C, Y. And so our pull-up network is going to be 3 transistors in parallel. So we get A, let's draw them all in the same direction here. B, C, and Y. So it's not quite as interesting as I had hoped it would be. But you get the general idea. We can basically use some Boolean algebra if we like to find the conduction conditions for the pull-up and the pull-down networks, and then we can read the network topology directly off of the Boolean expression, remembering that conjunction, which is AND, corresponds to series connection, and disjunction, the plus, corresponds to parallel. Okay? So let's see if we can't go the other way. Suppose I just draw some pull-down network. Let's make it a series transistor here with these 2 transistors in parallel. And maybe this is A, B, and C. And I want to know, what does the pull-up network look like? That would be appropriate for this gate. So there's going to be A, B, and C going in here. But what does this pull-up network look like? That would be appropriate to complete this combinational Cmos gate. Well, we know to approach this problem, we can say, well, we can write down the conduction condition for the pull-down network. So we know that D is going to be, well, we have A or B, that will be the conduction condition for this piece of the network, in series with C, or ANDed with C. So that would be A or B conjoined with C, like so. And this, if we recall from our previous discussion, should be Y bar. Okay? That means that U should be the complement of this. And so we can take this A, U should equal Y, which means this should equal A or B ANDed with C with an overbar over the whole thing. And so again, we can use De Morgan's law. We can push this down one level and write this as A nor B ANDed with C bar. I'm sorry, AND becomes OR, and so this becomes ORed with C bar. And now we can use De Morgan's other law and push this down one more level so that we have the complementation directly on the Boolean variables. And so this would become A bar and B bar or C bar. And now we're in a position, this is in a form that's directly implementable as a PMOS pull-up network, because we have these three Boolean variables with the bars directly on them. That's implemented directly by the PMOS transistors. And so the pull-up network would look something like this. We would have the A transistor and the B transistor in series, and that would be in parallel with the C transistor. And so we'd have something like A, B, C. Okay, so the pull-up network looks like this. Now, there's a way that's fairly straightforward to directly read this network, which is called the conduction complement of this network, directly off the network topology without having to go through writing the Boolean expression and then applying De Morgan's law a bunch of times. So the basic idea here is that stuff that was in series becomes in parallel. So corresponding parts of the pull-up network and the pull-down network that were in series become parallel, and things that were in parallel become in series. And also NMOS transistors become PMOS transistors. So here we have the C transistor in series with the A and the B transistor, which are in parallel, so that this series arrangement has turned into a parallel arrangement. And then for the A and the B part, that parallel arrangement has become a series arrangement. So you can go directly synthesize PUN from PDN directly, or vice versa, by interchanging NMOS and PMOS. And series and parallel. maybe should say NMOS and PMOS series in parallel. So let's try a different example. Suppose I were to give you a pull-up network, like, I don't know, and say, what does the pull-down network look like? And so this is, let's say this is A, B, C. I'll skip D. It still wants to be a PMOS transistor. Call this E and F, since D denotes our pull-down network conduction condition. So we've got A, B, C, D, sorry, not D, A, B, C, E, F. All right, well, we're going to directly synthesize the pull-down network from the topology of the pull-up network. So first of all the PMOS transistors will map into NMOS transistors. And I've got A and B here in one branch that are arranged in series. So that's going to be a pair of transistors in parallel. So that piece of the network would look something like this. So A and B, which were in series, become in parallel. Okay, that was in parallel with this thing. And so that's going to map into this piece being in series with the part that corresponds to this piece. Okay. So the piece that we have to design here is going to have itself two things in parallel, because we got the C thing in series with this subnetwork. So the C thing is going to be in parallel with the E and the F thing. All right, so here's the C thing. That's in parallel with the thing that corresponds to E and F. Well, E and F are in parallel here, so they're going to have to wind up being in series over here. So here's E and F. So here's the pull-down network. So we basically have swapped things that were in series for things that are in parallel. We swap things that are in parallel with things that are in series. Here, these were in parallel. The corresponding thing is in series. These were in series. They become in parallel in the pull-down network. And of course, you can verify this through the Boolean algebra. And if you're more comfortable using Boolean algebra than going directly from the network to the network, that's fine. There's nothing wrong with that. It takes a little bit of practice, but sometimes it's just more convenient to read the answer right off the topology of the network. Okay. let's look at I'm going to spend a little time looking at the a couple of maybe more interesting examples. One is two-input XOR. So XOR is exclusive OR. So this is true when either A and not B or B and not A. So in this case, Y is equal to A B bar or A bar B. And the logic symbol and the truth table for this function are as follows: A, B, Y, is 0, 0, 0, 1, 1, 0, 1, 1. And we have 0, 1, 1, 0. So exclusive OR means that the output is true when either A is true or B is true, but not both. And so this has this kind of logic gate symbol. So it's like an OR with an extra little curve back here in the back end. So in this case, we're going to find that we're going to need A in its complement and B in its complement as well. So the conduction condition for the pull-up network would just be U equals Y. And so that's AB bar or A bar B. And no amount of applying De Morgan's law is going to get us in a situation where we have both of these occurrences of A with an overbar or not. So D is going to be Y bar, and we can write that as A B bar or A bar B overbar. And I mean we can push this down one level and write this as A B bar bar ANDed with A bar B bar. We can push it down another level and write this as A not A or B ANDed with A or not B. That might be a convenient form to have it in. And so what this would look like is something like, so we've got two branches in parallel for the pull-up network, each with two transistors in series. So we have here two transistors in series. They're Pmos transistors, so they have a bubble on the gate. And we're going to have, let's see, if this is the A, B bar branch, we're going to have A bar and B, because we have to, so we have A complemented so that when we go into the bubble, it's A, and B goes in directly because it's got a bubble in the gate. And so this part would correspond to A B bar. And the pull-down network would be a series combination of two transistors in parallel each, so that would look something like this. So A bar B. We've got A B bar. And then the output of the gate here is Y. And we're going to need two inverters to generate A bar from A and B bar from B. And so this is a little more complicated gate. Here we have 8 transistors in the gate plus 4 transistors in the inverters to generate the complements of the input signals. And so the Xor gate is actually used quite a lot in generation of parity bits, and it also factors into things like adders, and it's just a generally useful kind of function. But you can see it's a little bit more complicated, and it's also not something that's nicely implementable because you need signal and complement all over the place. Okay, so I think that's going to be it for this one.